Matt and Taylor, can you hear us?
Yep.
Excellent. All right. Okay, well, as you may well know, registration opened up for spring not too long ago. So if you need the second half of this class, which I believe everybody does, I think that was the case when we talked about at the beginning of the class. But if you need to take the second half of this class, this is the time to sign up for it. 2120 is the second half, 2121 is the lab. In the second half of the class, just for your information, we'll be studying electricity and magnetism. And yeah, that's what we're going to be doing. So, yeah, as far as how that class generally goes, in that class we use many of the things that we used in this class. We'll be using the ideas of forces and energies and other things like this. We have far fewer, I think there's fewer subjects that we really get into in that class because it really is mostly electricity and magnetism. That's pretty much all we do in that second semester. I would say most students, I think, find that class to be about the same level of difficulty as this class. Some people find it a little easier, some people find it a little harder. It's just kind of a personality thing, I think. So many of the things that we do in the second class are non-intuitive, but maybe easier to gain an intuition for, is maybe a good way to say it. I don't know. So yeah, what?
What's the difference between NP01, 010, NP01A?
So 010, the section 010 is the one that you will take if you're here in North Platte, taking it in classroom. If you're taking the class over Zoom, then you'll sign up for 01A for both the class and the lab. That makes sense. But the lab's NP, it's physics, it's PHYS 22121. So make sure you get signed up for that. And we can get you done with all your physics requirements as you move on through your education, which I think you'll find to your advantage if you end up taking physics at a big university, for example. You're usually in a classroom with like 300 or 400 engineers, which is not a bad thing necessarily in itself. That's how I took the class. But the downside to that is that you usually have very little access to the professor. The professor has so many students and not enough time for all of them. So you end up spending most of your time with a teaching assistant, a student teaching assistant, which also is not necessarily a bad thing, but it's, I think, maybe not as good as having access to the actual teacher of the course. Also, that tends to make the class a little more competitive. They tend to make the class more competitive in the university environment. I think that that's changing nowadays. It was changing a little bit when I was in school as well, but the competitive environment for me was never one that I thrived in educationally. It was just annoying to me. So anyway, that's just for your information. The class will continue along in the same kind of vein where we will discuss things and talk about things in class and do little demonstrations here and there. Homework and labs and tests will all be on my Open Math. And labs will be done at home. I will be adding some equipment. I will be adding at least one other kit to the kit that you already have for the lab stuff. The second kit will have some things that you can use with your IO lab to do some electronics stuff, electricity and magnetism stuff, but it will also include some other things that you will use outside of or in addition to your IO lab. And last year I added 2 kits, but I think this year I'm going to combine them into one. I don't think we actually need to have 2 kits. So we shall see how that ends up, but that's kind of how I'm thinking here as we get ready to sign up for that class. Let's see, what else do I need to talk about? Oh, also for next semester, if any of you are interested in engineering courses, I don't really offer many engineering courses each semester. Next semester I offer one, and it is a programming course. And at this point, I think I'm actually going to, I've been researching options for changing the programming course because I used to teach it using MATLAB, which was a pretty standard programming language used by engineers when I was coming up and when I was going to school. And it still is pretty standard today, actually. But it's expensive. To buy a student version of it is only $50, I think, maybe $100 at most. But you know, universities have to pay thousands of dollars to use it, and companies have to pay thousands of dollars to use it. So over the past several years, even probably 10 or 15, 20 years, a new programming language has emerged that is an open source program called Python. And I've been thinking of ways to switch over to teaching my programming class using Python. I've had some experience with Python over the past few years as well, so I've got a fairly decent handle on its fundamentals. I'm not a great programmer, but I don't pretend to be. I just try to facilitate students as they try to learn about programming. But anyway, the great thing, of course, about Python is it's completely open source and free. All the tools and everything are free unless you want to pay for some thing that is available out there. But it's not. You don't need to pay for anything if you don't want to. You can do anything you want with it. It's also very easy programming language to use, but it's by no means the only programming language people do use in science and engineering. So as I've been looking around for ways to approach this class, teaching it from a Python point of view, I actually came across something that I'd heard of before, but I'd never really looked into much, and that is Harvard has a free course for teaching programming that you can take, and it has a bunch of lecture videos and demonstrations that are online. And I started looking into that and started watching those lectures, and I actually found them really quite good. The professor that teaches this course at Harvard is a true professor of computer science, and so he is an expert in the field. And he's also very engaging. He's been teaching this class for a long time. So he's come up with some really great resources for it, including some really innovative ways to teach programming. I teach programming in a similar way that he does, but he has many more resources at his fingertips. He has lots of money to develop these resources and so on. So what he does is he starts teaching programming by not teaching a language from the very beginning, but teaching how computers work, how humans interact with computers, how other computers interact with other computers, how the internet works, how applications work, so on and so forth, you know, how memory works. And that's the same way that I do it. But he has some great tools that are within this class. So not only are these lectures free, but you can actually sign up to take the class for free through edX, which is an online course system. And then through that online course, you get access to all of these resources and everything that he's developed for this course, which is great. And I'm actually taking the course now to see how it is, to see if it will work for us in next semester. But if it looks good to me, what we will do next semester for this programming course is we will just all sign up. All the students will sign up for this free online course, and we'll go through it together. And that way I'm there for you if you have specific questions that you want to ask me. Of course, you can ask questions online on the online course as well, but we can have interactions and we can demonstrate things specifically in class, and we can go through this class together. The advantage of that is, of course, you have access to the resources that he's developed, but you also have access to a Harvard taught course, which is nice. And you can even get a certificate for taking that course, which you can put on your resume and which will be very useful as you go forward in your life, especially if you're interested in programming of any kind. Even if you're not interested in programming, if you're going into science and engineering, you should know that you will be required to take a programming course at some point in your life. All scientists and engineers do. And I mean, a very few don't, but it's getting pretty rare these days. Even biologists have to take programming courses, and biologists use Python a lot, actually. So anyway, it's something that's a very valuable skill, and it's almost always a big factor when you're going and looking for a job. This kind of the skill of being able to program something using programming languages that are useful in science and math, or science and engineering and math and everything else. They look at that. They look at that specifically in resumes, and they look for that experience, because oftentimes when you're coming into a job, you're tasked with doing the programming. A lot of the people that have been in the business for a long time have maybe been in it so long that they're not up to date on programming, or they've never done any programming, and so they need people to come in and play that role. And you know, anything that you can do to get into a job position and get your foot in the door is useful. So anyway, that's kind of the direction I'm going with this new design for this course. The course only meets once a week. We meet for 2.5 hours, I think, once a week from 1 to 3:30. We don't always use all that time, but the idea of that is that learning a programming language is learning to program in general is much like learning a language, and time matters. You have to spend a lot of time every time you study a language to kind of program your brain to work in that language. With programming, you're trying to communicate with a computer and make the computer communicate back. And so it's very similar. And the more time you spend doing it, the better you get at it in chunks. It's better to spend 2 or 3 hours all at one time than it is to spend 1 hour a day for 5 days or something. You get much more out of it. And so that's why I do it on a Wednesday. I think it's from Wednesdays to 1 to 3:30 or something like this. But anyway, and I also teach that class by Zoom. I teach it as a podcast for students that maybe can't make that time but still want to take the class. That one is Engineering 1020, Engineering 1020. It's called Programming and Problem Solving, I think. And it's a good class, a required course for many science and math majors, and engineering majors for most of them, in fact. Let's see, what else do I want to talk? Oh, I also coming over the Christmas break, if you're in engineering specifically, I'm teaching, or if you're interested in engineering in any way, really, I'm teaching a computer-aided design class where you learn three-dimensional design. The advantage of taking this class also is it actually will fulfill a visual arts requirement if you take it. And so if you need to take a visual arts class to graduate, which sometimes you do, you usually have to take some kind of arts class to graduate, that will actually fulfill that requirement. That's pretty common in engineering schools, where the engineers, instead of taking, like claymation or underwater basket weaving or something, they take computer-aided design or three-dimensional design course. And that course is taught completely online over the winter break. It's a 4-week-long class. And you think, oh man, that's going to be super intensive. It's actually not that intensive. Essentially, I've given you a whole bunch of, there's essentially this online course that was developed here in Nebraska by a teacher in somewhere, I don't remember where. And as I was trying to get away from using textbooks to teach three-dimensional design. And so I was looking for online resources, free online resources. And he actually offered he offers his resources for a one-time fee. So I paid for these resources a few years ago, and you guys don't have to pay for them all because I've just posted them online. So all you do for this class is you get online every day or however often you want to. It's completely, the schedule is completely up to you as long as you finish the stuff. And you go through these exercises and you go through this material and you learn, essentially you're immersing yourself in the environment, designing things in AutoCAD. We use AutoCAD for that, which is not open source, but I believe it's free for students. So I don't think you have to pay for it. If it's not free for students, you can get a free trial for a month, which is the entire length of the class. So you're good to go. But AutoCAD is kind of the standard in the industry out there for civil engineers and most mechanical engineering things as well. It's a very powerful program. You just learn how to use it. You start off making very simple shapes and very simple parts, you could call them. And you progress until you can build like an entire house with its furniture and everything in it, windows and doors. And there are no exams in the class. They're just a bunch of little small quizzes and checkpoints and projects that you do. So that's what that class is all about. Did you have a question?
Does anybody else sign up for classes right now?
Yeah, I think there are at least like 2 or 3 students signed up for that class at the moment. Whether or not the class gets big numbers in it, I will teach the class. That's just how I do classes. I teach classes that students need when they need them, whether or not I can get enough numbers for them. But
do either of those courses require a certain computer?
you do need a computer for the AutoCAD core. Actually, for both of them, you need a computer that you can download things to. So you can't use like one of these netbook Google things. But besides that, it doesn't matter. Anything running Windows or Linux or Macs, all of them will work with all of those programs.
Okay, our school provides Chromebooks. That probably wouldn't work. So should I just use like a laptop at home then?
Yeah, the Chromebook won't work, but
okay.
your home laptop. And for the one in the spring using Python, I believe they do actually have an online Python compiler that you can use, but it's not fun. It's compiling programs online is slow and quirky and messy. I wouldn't recommend it. At least it has been in the past. I don't know if it still is, but AutoCAD, I believe they actually have an online AutoCAD design kind of environment, but again, I think it's slow and I think it's very limited. So yeah, I think that you can do it with a Chromebook. I don't recommend it. It's this kind of work on a computer generally requires you to have a fair amount of power at your fingertips, and so you don't want to be hooking onto the internet and trying to share that power with a million other users or whatever. So.
Yep. Okay. Thank you.
Let's see. Any other questions regarding these 2 upcoming classes besides the physics? And we have the 3 upcoming classes. We have the second part of physics and then these 2 engineering courses. Anything else? All right. For your information, I do offer a statics course in the spring for people going into mechanical engineering and civil engineering. I do offer it. I don't know if it's in the schedule right now, but I very rarely have students that are ready to take that class because you have to have taken this class before you can take that class. But you do not need to take physics 2 before you take statics. But if any of you are interested in mechanical or civil engineering, statics is a required course. And once again, I have developed that course completely from free materials. And that one was actually kind of difficult to create from free materials because it's pretty standard to have a textbook involved with that class. It's very standard. However, Carnegie Mellon University developed an online course that requires no textbook and is really quite good. And that's the one that I use for that course. It's got a great set of printed materials that you kind of read through, but within the printed materials, you're not just reading along and trying to decipher heavy textbook speak. Textbooks are really annoying when you try to read them for the most part. This one is written in much clearer, much cleaner, much simpler language. And it's not written in these super long chapters. It's like you read a little bit and then they do a little demonstration of it, and you participate by doing this online kind of stuff, these online activities that help you to understand the concept. And then you read a little bit more and you do another one, and then you read a little bit more and maybe there's a video, and then so it's got a lot of interactive stuff in it. All of the assignments are built right into that system at Carnegie Mellon. If you're not familiar with Carnegie Mellon is one of the big engineering schools in the world. They're in, where's Carnegie Mellon? Can't remember where it is, Indiana or something. But anyway, is it in Pennsylvania? Yeah, if it's in Pennsylvania, it's in Pennsylvania. I knew it was somewhere east of here, but I can never keep them all straight. But it is a great university, great at engineering, one of the top ranked universities in engineering. And this guy created this, not this one person, but probably several people created this great resource. And so that's another one, but it's completely free. So you don't have to buy a textbook, which is great because statics textbooks are like $300 or $400 a piece. And once you have access to it, once you sign up for it and take the class, you can actually go back and use the information there for reference or everything, just like a textbook. You'll have access to that forever. So that class is available. And if you're interested in taking that class, because you're all in this class, you will qualify to take that class next semester. So if you're interested in taking that class, just tell me and we'll set it all up, and we'll get it in the schedule. And just as a quick reconnoiter here, is there anyone who's considering that? You are for sure. Okay.
The course of the next semester is going to be pretty substantial compared to this one, so I don't know myself.
So that class has some fairly difficult assignments. I also the exams for that class, I use exams from UNL, because in order for it to transfer to UNL, you have to pass their exams. So I use the exams from UNL, and those are also in a free system. And it's a fairly difficult class. Essentially, it's this class, but it concentrates solely on the section of this class where things are sitting still and there's different forces on them, they're not moving. So it's Newton's second law, where force times mass equals 0. Sorry, where mass times acceleration equals 0. So it specifically focuses on that situation, but it goes into great detail. So it goes into detail with bridges, and detail with structures and other things, and it goes into a lot of detail with it. And so you learn a lot more about that. Whenever you go into detail, the math gets harder and more complex. However, I would say that the average student probably spends less time on that class than on this class, because they've already got a strong foundation of the understanding of the physics and everything. Really, it's just applying it in different situations. So they spend probably less time on that class. The other thing about that class is I also teach it as that one is essentially taught. I don't teach the class in class. It's always independent study. And if you have questions, or if you want to come in and get some extra instruction, you just tell me, and we schedule a class time together. And that can be with one student or 2 or 3 students at a time, or whatever. But that one, you're just kind of going through this online course, and then coming to me if you need help with it. Because it's taught that way, I let you do it at your own pace. You can do it. Some people will do the whole thing pretty much over the spring breaks when they don't have anything else to do. They'll just crank out as much as they can then, and just do little bits and pieces the rest of the semester and finish it up. Some people like to save it, to the end of the semester. I don't recommend that. But most people have just work on it a little bit here, a little bit there. And then when other classes are a little bit when their other classes have less going on, they'll concentrate on that one for a little while. And so that's the way I've taught it. I had a great amount of success with it. Almost, I think I may have had one student fail the class over the years, and I think they just put it off till the very last week, and they just ran out of time to get it done. And it wasn't even because they weren't capable; they just put it off way too late. Even though I kept reminding them to get some more done and trying to help them. I think everyone else who has taken that class has at least gotten a B in the class. Most people are getting A's in the class because the material is really quite good. It's, if you go through the material, you work through the material, you're going to learn it. It's really well done. So anyway, so that's called, that class is called engineering statics or engineering mechanics statics or something like that. Yes, it is engineering 2020, 2020. And that class is specifically designed to transfer to UNL, UNO, UNK even, I guess. UNK has kind of an engineering program where you start at UNK and then you finish at UNO. So if you're starting here, you're probably not going to go to UNK to finish your degree in engineering. But it is designed to transfer to UNO and UNL. And it should transfer pretty easily to any other university that is an engineering school. So that is available if you would like it. I will go ahead and get it put in the schedule since we have at least one student that's possibly interested. It's a 3-credit course, just in case you're wondering. And that is it as far as things that I wanted to talk about business-wise, school-wise, before we get started on physics. Any final questions before we move on to what we're doing today? All right, so we are moving on in chapter 7. We started off talking about work, where work is equal to force times distance. And then if you have a force that changes in different places, you know, the forces are bigger in one place and smaller in another place, then you have to start doing an integral. And the reason is because the work is dependent on the distance that you travel, which really means that the work is dependent on the path that you take to do the work. So, for example, if I am going to push a wagon from here to the bathroom or something in the building, somebody who goes directly down the hall in a straight line pushing the wagon is going to apply a certain amount of force for a certain amount of distance. But if I instead carry the wagon down the stairs, push it all the way around downstairs, carry it up another staircase, and then push it all the way around the building to the bathroom, I will actually end up doing far more work because it depends on the path you take. The force that you apply matters, but that force can change if you take a different path. And also, if the path is longer, you're applying the force for a longer amount of time, which means you're expending more energy, right? And if that force is changing during the path that you take, you need to know how it's changing, and you need to adjust that so that the amount of force matches up for the type of the part of the path that you're in, and that will change the amount of energy that you exert. So, for example, carrying or pushing the cart up and down the stairs is going to require more energy per inch or per foot than pushing it along a nice flat smooth surface. And so you're going to do more energy as you do things like that. So anyway, work has this path dependence, and that if that force is changing over that path, you're going to have a force that's depending on the path as well, and then you're all of a sudden in integral territory. And that's what we're doing here in this part where we left off. We have this example where they tell us right at the beginning here, they tell us that the path has this function y equals 0.5x squared that defines the path, that tells us that the path is a parabola. This is the picture of the path. And they also tell us that the force changes as it moves along that path. And they give us a function for how it changes. This is a function of y and x. It's 5 newtons y I hat and 10 newtons x j hat, right? And what that means, what this function means is that this force, when it moves in the y direction, changes by 5 newtons every meter. If you move upward, it changes by 5 newtons every meter you move upward. But the force changes not in the y direction, it changes in the x direction. So the x component of the force changes as you move in y, as you go up. And the y component of the force changes by 10 newtons per meter as you move in the x direction every meter. But that's the y component of the force. So the y component of the force changes as you move in x, the x component of the force changes as you move in y. And you think, well, that's super confusing. It is. It's super confusing. There's no question. But I guarantee you that in the real world, forces and things are super confusing. There's no such thing as just a simple thing going on in the real world. Things are not simple in the real world. The great thing here is that they've given us the functions, and all we have to do is the math. The math is actually fairly easy. What we know about the math of function of work is that it's the dot product between the force and the path, essentially. And so we've got to do a little bit of work before we do that. The dot product is going to require us to understand what each step of the path is. So what we do is we take the equation of the path. Our equation of the path was this one, y equals 0.5x squared. We're going to take that and we're going to break it down into tiny little pieces. Well, we do that by taking a derivative of the path. So we take our function y equals 0.5x squared, take its derivative. dy is going to equal 2 times 0.5x dx. So you take the derivative of that function. That derivative is the thing that we're going to integrate over. That's going to be our dy. We're going to have f dx and f dy. Is we have to do it in two of them because our force has an x component and a y component. So our force part, our x part of the work, the part that the x forces contribute to the work is going to be f sub x dx, or the x component of the force times dx. That's the dot product. That's where we get the dot product from. And then fy dy is the second part of the work that comes from the y component of the force. If you want to know how we got to this point, we can write that out here. Did I share my screen yet? I didn't. I'm totally realizing I didn't share my screen. You guys aren't seeing what I'm seeing. I need to. Yeah, you guys are saying, what is he talking about? Sorry about that. I think I'm recording. Let me check to see if I'm recording. Looks like I'm recording. I hope I'm recording. You are screen sharing. Am I recording? End meeting. Yes, I am recording. Good. Okay. Good. All right. So anyway, we can actually do this math really quickly. It's not that hard. The work is equal to the integral of the force function dot product with the derivative of the path. So dr here. Our path was this function here. So we took the derivative of this path to get dy equals x dx, right? And so essentially what our dr is, our dr has the vector that we have here for dr is going to be dy sorry, it's going to be dx plus dy. It's going to be dx x hat or I hat plus dy j hat. There we go. That's what it's going to be. Because we're in 2 dimensions. And we figured out what dy is. We know what dy is. It's related to dx, which is good because we don't want to have to do 2 things differently. But dx is just dx and dy is 2 times 0.5, which is just 1 x dx, right? So that's our dr. When you do the dot product of the force and the dr vector, you get the x component of f times the x component of dr. So the x component of f is f of x, and the x component of dr is dx. And of course, the I hat dot I hat becomes 1. And then fy dy gives us the y component of the f times the dy, which this is the dy, right? And so that's what they get here. Get 5 newtons per meter y dx. That's our component. That's our x component. 5 times y, 5 newtons per meter times y is our x component of the force. And then the dx is the x component of the dr vector. And then this right here, 10 newtons per meter times x, is the y component of the force. And then we're multiplying that by the y component of the dr vector, which is dy. And then they're going to plug in the y into this one. What is y? Well, y is right here. So they're plugging in y. They're plugging in this thing right in here into y. And that's what they get here. The x squared and the 0.5, that's what that is right there. That's what y is. And then they have the dx. And then they're plugging the dy in right there. And the dy is the 2 times 0.5, which is just 1, 2 times 0.5 times x dx. This one already had an x in it, so it ends up being x squared. So one of these x's came from the dy, the dx came from the dy, and the 2 times 0.15 came from the dy. Now this is great because now both terms are in dx. Both of them are in dx. Both of these have x as their variable. So we can integrate both of them together. In fact, we can add them both together to get one simple term. It actually simplifies this term down quite a bit. Man, this is giving me trouble. So now we've simplified this down. It's just this 12.5 x squared dx, and that's what goes in our integral for this f dot dr. We've done the dot product. Now we put it back into the integral, and we integrate this to get our work. Right? Now that we've integrated, now we've put together our integral, which is really the hard part. The hard part is figuring out what that integral is by going through this process of taking the derivative of our path, doing the dot product with our path with the force, and then putting that into the, and if you have to build those functions yourself, it gets a little more complicated, but we'll get to that in a minute, or a few minutes. Anyway, so we do our integral. We're going to travel along in x from 0 to 2 meters because they told us to. And this is the thing we're integrating. The integral, again, is just the inverse of the derivative. So the integral of x squared, you take that 2 and you add 1 to it, and then you divide by that number. So that's x cubed divided by 3 in the end. The constant comes through. And then you evaluate this between these 2 points and take the difference. You start with the top one, evaluate it 2 meters, plug in 2, you get 8 over 3, and then you evaluate it 0, you plug in 0, you get 0. So it ends up just being this. If this wasn't 0, if this was from 1 to 2 meters, you would evaluate it at 2, get 8, you'd get this 12.5 times 8/3. Then you'd evaluate it at 1, you get 12.5 times 1/3, and you would end up subtracting the bottom one from the top one. So you take the 12.5 times 8/3 minus 1/3 quantity. Anyway, so that's the integral, and that's the now that gives you the work done. And you can see that the integral really is the easiest part. It's really just setting it up. That's the
setting up. I was like looking at it while you're talking through it. I understand it, but that was ghettos. I've never seen anything like
yeah.
that.
It seems like you're like, oh, I'm just doing things and slapping it together, right?
Specifically, the force being divided into 2 different, the x component and the y component before the problem started. I've done problems where the force wasn't divided, but then you were putting them together to both be in terms of x.
Okay, so let me do it separately on a whiteboard here.
And like I understand it, it was just like
let's do it separately on a whiteboard so you can see why we're doing it. I'm not going to actually do the math. I'm just going to show you the method, the thought process of why we do this. Okay. So in any given situation, when you're dealing with the work is always going to be equal to the integral of the force vector dot product with your path vector, the path that that force acts over, always. Okay. Now, the work, if you notice, has no vector over it. This is going to give us just a number. That's because the dot product gives you just a number when you take the dot product between two vectors. It doesn't come out as a vector, it comes out as a number. What are we trying to do here? Well, what the integral does is it adds things together. What the derivative does is it takes something big and breaks it into little tiny parts. So you've got this path that you're taking, that you're applying a force along this path. And maybe right here, the force is this much in this direction. And maybe over here, it's this much, maybe it's smaller and going this direction. And maybe over here, it's way bigger and going this direction, and so on and so forth. So the force is changing direction and it's changing magnitude, it's changing all the time. So what we need to do is we need to break down this thing into little tiny steps, and we need to know the force at every little tiny step and the direction that we're going at every little tiny step. And that's what the derivative is going to do. It's going to break it into tiny steps, and the integral is going to add all those tiny steps together in the end, right? So what we would like to do is make this so that it's doable. This becomes doable, an integral becomes solvable, or when it becomes simple, essentially. You can take a derivative of any function, but you cannot take a derivative or take an integral of any function. Integrals are much pickier. There's a very few finite number of integrals that can actually be done. Most integrals cannot be done. Most functions you cannot take an integral of. So we need to figure out if we can create a simple integral or a simple function from this dot product that can be solved. Well, if they tell us the function of the force, and they tell us something about the path, a function that defines the path, then we can go ahead and take that dot product, right? We can do the dot product. Well, our force vector has a x component, f sub x, and it has a y component, f sub y, and this is what the force vector looks like this, right? And our path vector, in this case, our path was a function that looked like this: y equals something times x, you know, a bunch of stuff with some x, it's dependent on x in some way. But it wasn't written necessarily as it wasn't necessarily written as a vector. But that's okay, because in this equation, dr is defined more by your coordinate system than anything else. So dr in two dimensions, if we're gonna look at this as x and y, which is what we're doing, then dr is always going to equal dx I hat plus dy j hat, and if it has a third dimension, then plus dz k hat. The hard part is figuring out what these things are, dx and dy. Well, they've given us something that tells us what y is. So to find out what dy is, I just need to take a complete derivative of this. So in the case that we were in, y was equal to, what was it equal to? 0.5 something. What was it y equal to?
Y is equal to 0.5 x squared.
X squared, like that?
Mm-hmm.
So y was equal to this in this particular case. So to take the derivative of y, it's just dy, because it's a variable. You know, it's an actual variable, so you're just taking dy. To take the derivative of this thing, you take 2 times, you take the 2 out of the x, right? And then 2 times 0.5, and then x. But you also have to take the derivative of the x separately when you're taking a complete derivative, because we're not doing the derivative of y with respect to x. We're doing the complete derivative of both sides of this. So if you remember that from your calculus, that means that you also have to take the derivative of the x separately. And so you have to put the dx in there. If you were doing dy dx, it would be like dividing both sides by dx, and then it would just be that. But we're taking the complete derivative of both sides We're not doing dy dx, so it ends up being 2 times 0.5 times dx, which means that dy, and I would take this extra step if I was doing the problem, 2 times 0.5 is just 1, so dy is going to be just equal to x dx. That is important because that goes right there. And because we've written dy in terms of dx, then we can leave dx as it is. This dx right here can stay because now they're both in the same realm. We're taking the derivative along the same axis. And that has simplified our integral and made it doable, right? That's one of the things you're trying to do, is you're trying to make both terms integrating in the same thing. We want to make them both dx or both dy. And you can do it the other way. You can make them both dy if you want. You could solve this thing for x and take, take the derivative and give you a different answer, but you can still do it. It would give you the same answer overall, but it would give you a different integral. But it would give you the same problem in the end. So now that we know this, we can construct our dr. We construct our dr thing. Our dr vector is now equal to dx I hat plus x dx j hat. This vector is our dr vector. This vector is our f vector. Now you can do that dot product. When you do that dot product, you get fx dx plus fy x dx. And we know what fx and fy are, right? So we go ahead and do that next step. The next step says that, what did I just do? There we go. The next step is we're going to do f dot dr, and f is equal to f of x I hat plus fy j hat. And then we're going to do the dot product with dx I hat plus x dx j hat. And with the dot product, you take the I hat stuff and multiply them together. So we get f of x dx. And then you add that to the y, to the j hat stuff multiplied together, fy x dx. Well, f of x, we know whatever that was. What was f of x in this problem?
What was f of x?
Yeah,
F of x is 10.
it's 10 times y, right?
10 times x dy.
No, what is the I hat component of f, of the force?
It's 10. The I have. Sorry, no, it's 5. I'm sorry.
It's 5 times what? There's a variable there.
5 1.
It's 5 times y, right? So it's 5 times y dx for the first term here. And then the second term, fy, is 10 times x, right? So we get this. This is what we get in the end. That's our dot product, right? And then we also know what y is. They've told us what y is, so we plug that in. Y is equal to 0.5 times x, right? So we now have this. And we also know that x times x is x squared. So now we've got our thing here. This ends up being 5 times 0.5 is 0.25 x dx plus 10 x squared dx. And that's what's we're going to be putting in our integral, right? So this just ends up being a polynomial, and we know how to do that for polynomials. So anyway, did I do all that right? Did I miss something?
Like you said, I mean, it's just the setting up part that is
Yeah.
the difficult part. The integral itself is just x cubed
Yeah,
over 3, and that's,
yeah, it becomes very simple in the end. But following through the logic of why we do this, our dr vector has to be put into into a dx x hat, a dx I hat plus dy j hat form, because that's the coordinate system we're in. So that's what our R vector is going to have, that format. Then we got to figure out what is dx and what is dy. Are they related to each other? We have a function that relates them. So we turn the dy into a something dx. Or you could turn the dx into something dy if you wanted to. You could do it the other way if you want.
Could I also think about the x and the y components of force as two different equations, but since x was 5, or since y was 5 and x was 10, it's just, because I remember doing this in Calc 2 last year. I'm trying to think about.
So what you're saying is, can't I just do two different integrals, one in y and one in x?
No, I know I can't do that. There's a way to combine.
Why can't you do it? So why can't you do it?
Because you did just 2 different intervals, those are 2 different lines.
But they're also dependent on each other. That's the real reason that we have to do this. Because there's an x in the y part of the force, and there's a y in the x part of the force. So as you move in x, the y part of the force changes, and as you move in y, the x part of the force changes. So you have to do it this way because of that interdependency, because the force is dependent on the movement in 2 dimensions. That's the reason we have to do it this way. If this was in 1 dimension, then you wouldn't have any problem with that. But in 2 dimensions, and in fact, even if it was in 2 dimensions and the x part of the force only depended on the x movement, then you could do it as two different integrals. But because it's interdependent, because there's an x in the y part and a y in the x part, you have to do this. And so we generally just teach people to do this anyway, because then you don't even have to think about it. You don't have to think about whether or not there's interdependence. You just do it this way every time, and it always works out. So, any other questions on that? Let's see here. All right. So again, we've taken all of our class time, mostly because I spent it all talking about classes for next semester. Let's we need to go and change this. What is this? This is due when? Due Tuesday. So we've still got some time on Monday to hopefully get to the rest of this. The rest of this chapter is, I think it's going to be a lot easier because working through the integral of the work integral is actually the hardest part of this whole chapter. But I think we've worked through it enough that we should understand it well enough. Don't put off getting started on this homework. Get started on it right away so that you can kind of see the kinds of problems you can do. Once it starts talking about kinetic energy, that's where we haven't done anything yet. So we will cover kinetic energy next time and conservation of energy next time. And that should finish up chapter 7 for us. So have a great weekend. There is an experiment posted for this weekend. If you have any questions or concerns, make sure that you email me. Have a great weekend. Enjoy the nice weather. Might be the last nice weather of the year. Who knows? Is it going to be cold this weekend? I thought it was.
Supposedly not, but I don't trust it.
All right. Well, have a good one. We will see you all later.
Have a good weekend.
Thank you.
Have a good weekend.
Thank you. I have like the most polite students of all time this semester. Everybody always wishes me a good weekend and says goodbye. Most of the time, my Zoom students just kind of drop off the planet like sometime in the last 15 or 20 minutes of the class. It's kind of a nice change. I mean,